Everyone's calling it a $6.5 trillion discovery, and that number alone is enough to break people's sense of scale. Trillions of dollars locked inside rock, sitting quietly in Western Australia. Headlines make it sound like someone just found the largest iron ore deposit on Earth, as if it had been hiding there unnoticed until now. But nothing about this story involves stumbling across buried treasure. This discovery didn't happen in the desert. It happened in laboratories. Thin sections, isotope ratios, and one deeply uncomfortable realization. We may have been wrong about when the world's most important iron ore actually formed. For decades, the Hamersley province in the Pilbara has been the backbone of global steel production. It already supplies more iron ore than any other region on the planet. Entire cities, railways, ports, and national budgets have been built around rocks that geologists mapped generations ago. So when the media says new discovery, geologists instinctively roll their eyes. Nothing about the Pilbara is new, but that reaction misses the point. The discovery isn't about where the iron is, it's about what it really is, and more importantly, when it became ore. That distinction matters, because ore isn't just rock with metal in it. Ore is rock that has crossed the threshold where extraction becomes economically viable. Change when that threshold was crossed, and you change how much rock qualifies as ore. Scale that shift across the largest iron province on Earth, and suddenly you're talking about numbers that rewrite long-term supply models. That's where the trillions come from, not from new rock, but from new understanding. The shift began when researchers stopped relying on indirect dating. Traditionally, the age of iron ore formation in the Pilbara was inferred from surrounding sediments, volcanic layers, or regional geological events. Those methods are useful, but they assume the iron mineralization happened at the same time as everything else. The newer studies did something more direct and far more dangerous to old assumptions. They dated the iron oxides themselves. Hematite, the actual ore mineral. When those dates came back, they didn't line up with the established story at all. Instead of forming soon after the original banded iron formations were deposited more than 2.4 billion years ago, the high-grade ore appeared to have reached maturity much later, around 1.4 to 1.1 billion years ago. A billion-year difference. That's not a tweak, that's a rewrite. Once you accept that timing, a lot of things suddenly make sense. Features that never sat comfortably within simple weathering models snap into place. The depth of ore bodies, their structural control, the presence of microplaty hematite far below ancient erosion surfaces, the fact that some deposits appear unfinished, stalled at intermediate stages, while others pushed all the way to extreme grades. These aren't the fingerprints of surface weathering alone, they're the fingerprints of a system that stayed open, reactive, and fluid-driven for far longer than anyone expected. To understand how we got here, you have to go back to the beginning, not of mining, but of the rocks themselves. The iron ores of the Pilbara began as banded iron formations, or BIFs, deposited in ancient oceans between roughly 2.6 and 2.45 billion years ago. These were not biological reefs or sandy shorelines, they were chemical sediments, laid down in a world where oxygen was only just beginning to leak into Earth's surface environments. Dissolved iron was abundant in seawater. When oxygen levels rose, that iron oxidized and precipitated out, settling onto the seafloor in thin layers. Silica followed, then iron again. Over millions of years, this rhythmic chemical process built vast sheets of iron-rich rock, interlayered with chert. On their own, these rocks are unremarkable. BIFs occur on every continent. Most are low-grade, dense, and uneconomic. The Pilbara's importance comes from what happened after deposition, and that story spans more than 2 billion years. The first major transformation occurred during the Paleoproterozoic, when the region experienced large-scale tectonic deformation. Orogenic activity folded the rocks and created pathways for fluids to move through the crust. Deep basinal brines, hot saline fluids squeezed out of sedimentary successions, were mobilized and driven upward along faults and fold hinges. When those fluids encountered banded iron formations, they began altering them chemically. Carbonates formed where silica once dominated. Silicate minerals recrystallized. Magnetite grew, dissolved, and reprecipitated. These processes didn't create ore yet, but they did something just as important. They prepared the system. They increased permeability. They introduced chemical contrasts. They turned rigid rock into something that fluids could exploit later. This was the quiet groundwork stage, invisible on a mine face, but critical to everything that followed. Then the system rested. For hundreds of millions of years, the iron sat in place. Continents assembled, supercontinents broke apart, life evolved, and still the iron waited. The next major act is the one that rewrote the story. During the Mesoproterozoic, something reactivated the system. Large-scale fluid circulation returned. but this time the fluids were oxidizing, and their impact was transformative. Magnetite was converted to hematite, preserving its crystal shapes as martite. Goethite formed and was partially leached. Chert, carbonates, and silicates were selectively removed. Iron stayed, everything else went. This wasn't gentle surface weathering. Oxygen isotope data and fluid inclusion studies indicate temperatures exceeding 200 degrees Celsius in places, potentially much higher along major structures. These fluids moved laterally through faults, vertically along faults, and preferentially along shale layers and dolerite dikes that focused flow. The Pilbara became a massive interconnected fluid network, with iron formations acting as chemical traps. This is when the characteristic ore textures emerged. Microplaty hematite grew in thin flakes, increasing porosity and friability. Goethite appeared as an intermediate phase, then was leached away in most mature systems. Skeletal textures formed where minerals were selectively dissolved. Original BIF banding remained visible, even as the rock's chemistry was completely transformed. The ore didn't replace the BIF wholesale, it refined it. Not all deposits progressed equally. Some stalled, retaining significant goethite and lower grades, others advanced further, becoming the ultra-high-grade martite-hematite ores mined today at places like Mount Whaleback and Tom Price. This variation isn't random, it reflects differences in fluid access, structural position, and the longevity of alteration. In other words, geology mattered deeply. Only after all of this did surface weathering take its turn. During the Mesozoic and Cenozoic, long-term exposure near the land surface allowed shallow supergene fluids to further clean the system. Remaining goethite was leached, porosity increased, grades ticked up slightly more. But by this point the heavy lifting was already done. Weathering was the polish, not the engine. This multi-stage history explains why the Pilbara is unmatched. Plenty of places had BIF, fewer experienced deep tectonic preparation, fewer still were reactivated a billion years later by large-scale fluid systems, and almost none sat tectonically stable enough afterward to preserve the result. The Pilbara didn't just get lucky once, it got lucky repeatedly, across geological time. That's why the discovery matters. If the iron became ore much later than assumed, then similar processes could have operated elsewhere, in regions previously written off as too old, too deep, or too altered. It also means that parts of the Pilbara itself may still host concealed high-grade ore beneath cover, below erosion surfaces, or in structural positions not fully appreciated before. Understanding timing expands possibility. For the rest of us, this matters because iron underpins modern civilization. Every bridge, every building, every power station traces its origin back to iron ore. Australia's role in that supply chain shapes global economics, geopolitics, and infrastructure planning decades into the future. A revised understanding of how much high-grade iron exists and how resilient that supply may be isn't just academic. It influences everything from steel prices to national strategy. But there's a deeper lesson here, and it's one geology teaches over and over again. The most important discoveries don't always come from finding something new. Sometimes they come from realizing that what you thought you understood was only part of the story. The rocks didn't change, our questions did. The $6.5 trillion number isn't buried treasure. It's the value of timing. It's the price of patience measured across a billion years. And it demonstrates that Earth doesn't reveal its secrets all at once. It waits for us to ask the right question. And in this case, that question wasn't where is the iron? It was, when did it become ore? I hope you found this as interesting as I did. And as always, thanks for watching.
Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.